Hello, this is Phil Thomas from New Era Systems. As you know, we test just about everything that we get in here. I say just about. Some things we cannot test, but in this particular case, this is a Belcom 2-watt C-band BUC that we're looking at. And I was testing this a couple of weeks ago and I noticed something peculiar about it. I was comparing the output power at different frequencies and I noticed that there was a change. Let me explain. When I'm testing the large KU band or C-band TWTAs, it's very normal for the saturated power to change according to the frequency. For example, a 1375 could produce 350 watts before it goes into saturation. 14 gig could be 340, and the top end of the frequency range for a KU band amplifier, 14.5 gig, would produce perhaps 280, 290 watts. So there is a change in the saturated power or usable power across the frequency range of a TWTA. And I was curious to see if the same thing was true with a small SSPA, because that's what this Belcom BUC is. It's an SSPA and not a TWTA. And so here are the components that I'm using. The most obvious one right in front is the CDM570L modem. I'm using this to provide the 24-volt DC and the clean carrier and the 10 megahertz reference. The BUC itself is connected to a very large dummy load. This dummy load is capable of testing up to 350, 400 watts in C-band. But I don't have many other C-band dummy loads available. They tend to get sold before I can lay my hands on them. In this case, it's not for sale and I keep it well hidden. There are two test ports on it and I'm going to use those two test ports in the following way. One of them will go to the power meter, the other one to the spectrum analyzer. Input a level from the modem and look at the output. Then, without changing the power level, I'm just going to change the frequency and see what the power output looks like. And then I'll go to the upper end of the frequency range for the C-band BUC and do exactly the same thing. So I'll just be stepping through a low, medium, and high frequency range for the BUC and see if the power is consistent across the range. By consistent, I mean I don't have to tweak the power coming out of the modem. It gets whatever it gets from the modem and translates it to the appropriate RF power. Now I've got some cabling to do, so I'll be back in a moment with it all set up. This C-band BUC has a complete frequency range of 5.8 to 6.425 gig. But today I'm only going to test it from 5.925 up to the maximum 6.425 for a very good reason. This cross-guide coupler that I'm using is only calibrated from 5.925, that's on the low side. Although it won't make a lot of difference, in order to keep it as accurate as possible, I'm just going to stay within the range of the cross-guide coupler and not necessarily within the range of the BUC. Now I have everything cabled, but there's a couple of things that I need to do on the modem to make sure that the test works with the lockup converter. First I'm going to go to the ODU and I want to do two things. I want to make sure that the BUC has the 10 megahertz reference on. Yes. Now I'm going to go to DC power, make sure we have 24 volts. And it is on. And now finally I'm going to look at the local oscillator. I know that the local oscillator on this BUC is 4900 megahertz. And so that's what I've set in this modem. What does the local oscillator do within the modem? The answer is nothing. But it does allow me to see what the output, what the RF frequency is going to be. This modem only outputs L-band between 950 and 1750, something like that. It sends that IF frequency to the BUC. The BUC uses its local oscillator. It adds to the L-band signal and it produces the final RF signal. And by setting this up into the modem, I don't need to do a calculation, but I can see immediately what the output frequency is going to be. Now let's just go and look at TX. We're going to look at the frequency. And the frequency, the IF frequency that's being output to the BUC is 1525 megahertz. And that translates, using the local oscillator, to 6425, which is the top end of this BUC's output range. So C-band, upper frequency is 6425. Now the TX output level on the modem is minus 22 dBm. That's giving us 2 watt output. 2 watt output at 6425, the top end of the C-band frequency. This is a 2 watt BUC. It will go higher than 2 watts, but just for this test I want to compare the difference in output power across the frequency range. So you can see now it's running almost exactly at 2 watts. I'm going to change the frequency on the modem and I'm going to bring it down to somewhere in the middle. I'm going to call it 6225. Now if you watch this lower level, this is actually what the RF is going to be. There we are, 6225, enter. And on the spectrum analyzer you saw the frequency change. But what's interesting is that on the power meter you'll see that the output has jumped to 2.27 watts. Even though I never changed the input power, it's simply a factor of frequency with this particular BUC. So now I'm going to bring the frequency down to the lower end of the range at 5925. Again, you saw that frequency shift, and in this case the power has dropped to 1.82 watts. What I don't know is whether this is an oddity of this particular Belcom 2 watt BUC, or other BUCs behave in the same way. So what I'm going to do, I'm going to pull out a different type of BUC. If I've got another C-band handy, I'll put another C-band on there and I'll run this test again. If not, I'll put a KU band on there. So I'll be back in a couple of minutes with a different setup in place. Here's my next victim. This one is a super extended C-band 5 watt BUC. It would have been nice to have had exactly the same frequency range as the Belcom, but I don't have very many of the small C-band BUCs in stock. A lot of KUs, but very few Cs. This one has the, I think it's called the INSAT frequency. It runs from 6725 up to 7.025 gig, and it has a different local oscillator frequency that I have to set up in the modem to see the output frequency as I do it, as I make the test in 3 steps. Low at 6725, I'll go to 6925 and then 7025, and see whether or not the power remains constant at each one of those frequency steps. Okay, I'm back again. This time I've got this very high frequency BUC set up, ready to go. I've already changed the local oscillator frequency on the modem so that we can see what the output RF is supposed to be. Just for information, the local oscillator frequency is 5.76 gigahertz. So now I'm going to check the frequency. The low end of the frequency is 6725, so that's 965 megahertz output. And as you can see on the spectrum analyzer and on the power meter, it's outputting 4.45 watts. This is a 5 watt BUC, so you expect the output to be considerably higher than the Belcom that we were testing just a few minutes ago. So now I'm going to move the frequency from here up to 6.9, so that's the next increment that I want to work with. 905, 6.9. Enter. Frequency is shifted, and now we're seeing an output of 5.07 watts. So 5.08 watts. So again, it's shifted from 4.5 up to just over 5. Now I'm going to go up to the top end of the frequency range, 7.025, and see what happens here. Seven point oh 25, I'm there. Now the frequency has changed. Now the output power has changed again, dropping quite drastically down to 3.81. So this BUC made by NJRC is behaving in a similar fashion to the one made by Belcom. Belcom, of course, is made in Israel, NJRC in Japan. I don't know what difference that makes, but Belcom, the lower frequency was 1.82 watts, medium frequency 2.27, and the upper frequency 2 watts. So there was a spike in the middle frequency. This one, this 5 watt BUC, the lower frequency 4.48, mid-range, don't remember what it was now, but I think it was just over 5, and currently at the top end of the range 3.8 watts. So it's behaved in an identical fashion. In the field, I don't think this matters at all, because you have to set the power output to whatever the satellite operator requests. If you have to increase or decrease the power on the modem to get the exact power output specified by the satellite operator, that's what you do. And you don't worry about absolute levels, you just worry about what the satellite operator is seeing. So if you have to crank it up or push it down, that's what you do. I found this anomaly by accident. I didn't expect to find it. I don't know what it means. So if anyone has any bright ideas after seeing this video, I would be delighted to hear from you to see if these are design faults or design attributes, or that's just the way SSPAs work. Okay, that's Phil Thomas signing off.